to identify the extremum and the intervals of increasing and decreasing for a mathematical function without calculus, we could use the graph in order to find all this information, and that's what I wanted to show you guys how to do here. So let's say we were going to look at the function b of x, and we wanted to know, well, what is the minimum? Does it have a minimum? What is its maximum, etc.? And when is it increasing? When is it decreasing? And let's do all that at once. So first of all, we can always just graph it by going into y equals and typing in our formula. So this one is x cubed minus 8x plus 1. I'm going to go ahead and hit graph and see what I'm working with. And you might need to change your window around if you can't really see the properties that you care about. But when looking at this function, and we're going to talk way too much about polynomials fairly soon, so we're going to get into this stuff more. But notice what we have is, well, it's the general shape of a cubic function, which has a couple twists and turns to it. So it appears as though from left to right, it's going to go up, come back down, and go back up again. And we can see that it has an interval of increasing, decreasing, and increasing, and it has what we call a local minimum and a localized maximum and a localized minimum. Or sometimes they're called relative mins and max as well. But one thing that if we're trying to describe these things, it can be helpful to sketch. And in general, if you're working on an exam and you're using your calculator to help you solve things, I would generally create a sketch of what you see in your calculator on your paper, so that whoever is grading it, your professor, or same with homework, can figure out where you're getting your information from. But I can create a little sketch of my calculator, even graph some of the points. But basically, a lot of the key points that we're looking for are the tops and the bottoms of the hills, as well as when is it increasing and decreasing. And another thing I wanted to mention is there's a connection between the extremum and the intervals of increasing and decreasing. Because notice that when a curve transitions from increasing back to decreasing, in the middle we have a top point. Well, technically, point B on this graph was not the absolute maximum because point D appears to be larger. But the top of a hill is sometimes referred to as a relative maximum of the function, because in the immediate vicinity, this is a maximum. Same with C, where technically it's not the absolute minimum because this is smaller. In the immediate vicinity, this is the smallest value. And my point here is that relative mins and maxes, or localized mins and maxes, some books will call it one or the other, but it's synonymous, separate intervals of increasing and decreasing. So like going back and looking at this polynomial function b of x, we can see that there are 2 points. Here is a relative maximum, and here is a relative minimum. And those separate the function into intervals of increasing versus decreasing. And that's why it's helpful to find those first. That way you know exactly where you're at. So my point is, if I can find those 2 spots, I will know exactly when it's increasing, decreasing. So you might be able to eyeball it and say, well, it appears as though at about -2, we've got that little top of the hill. And we could always trace and hit -2 just to see. And if we actually do that, notice that my window is kind of hard to see because it's the mathematical formula for the function is getting in the way right there. But it doesn't quite appear to be the maximum. And if I change my range of my window to say maxing at x is equal to 15, oops, I want my y max to be 15, not x max to be 15. So I'll leave that right there at 10, and I'll change my y max to 15 just so I can see a little bit more of my graph. But basically, if I trace it at -2, I wanted to show you that is clearly not that point of the very top. So the next question you might be wondering is, well, how do I get the point? Like, you could always move your cursor by hitting left and right to try to see, and you could pick which one is on the top, but that is not a very accurate way of doing it. And your calculator actually can calculate very, very accurately what is that maximum point. Now, it won't do it exactly. The only way to do it exactly is with calculus. Well, not the only way, but you will learn how to do that in calculus. But for now, if we wanted to approximate that localized maximum coordinate, you can do that with your calculator, and it's above trace. Notice how it says calc right there. If you hit second trace, what this will do is it will have a calculate menu, which it can calculate things like minimums or maximums or zeros and other things. So since this point appeared to be a maximum value in the function, again, not absolute because it appeared to get larger over here, but again, it doesn't matter with the calculator. It will find either local or absolute maximums. Basically, I want to use this command here, calculate for maximum. And what happens next is the calculator, it's a little bit of a strange series of inputs to get it to find that point that you want. But basically how it will work is you need to tell it where to look. So basically what you want to do is you want to tell it what's a left bound, what's the right bound, and then give it your best guess in the middle. And what it will do is it will run an algorithm, which actually involves using calculus, to figure out, well, which one of those points is actually the top. And so basically notice, this is what you need to do. For left bound, you need to move your cursor a little bit to the left and hit enter. And that's just sort of saying, well, look in this vicinity. And notice it actually puts a little arrow there. Then it will ask for right bound, and that's where you want to move it a little bit of right of the hump and hit enter. And now notice that there's two arrows saying, okay, look in here. And then it will say guess question mark. That is what basically the calculator asking for. What's your best guess? What looks or appears to be the maximum. And then if you hit enter a third time, basically you need to hit enter 3 times. And once you do, it will calculate that maximum point to the best of its ability. And so basically I could come up with the coordinate. It will be more accurate than doing anything else. And it says that that maximum point is, I'm just going to use 3 significant figures, about 1.63, comma 9.71. And we would say that that is the relative or localized maximum. Again, those are synonyms depending on the book you're using. So that would be specifically that point right there. Okay, and then that we found our local maximum. Now, if we wanted to find our local minimum, we could do exactly the same thing. So again, if we go back into second calc, now use number 3, minimum. I need to do the same thing to find the minimum. I need to go a little bit to the left, hit enter, go a little bit to the right, hit enter, get right on it, hit enter, and we can get that minimum value, which is approximately 1.63, comma 7.71, negative 7.71, to give us that relative minimum. And there we have our mins and maxes. And now another thing you might be wondering is, how do I know there are not more mins and maxes outside of the domain and range that I have here? And really, you don't unless you really know the behavior of the function you're studying. So specifically with polynomials of degree 3, they can only have 2 mins and maxes at most. And there's reasons why, which don't worry about. But basically, this is one of the issues with the graphical approach is, well, we can only see so much. There might be more if we were to extend the domain range, but in this case, that's it. And then also, once we have those mins and maxes, it's a lot easier to describe the intervals of increasing and decreasing because, as we can see, again, it's always done from left to right. So moving down from the left side to the right side, we have an increasing interval up until this hump, then it's decreasing, then it goes back to increasing again. On the right-hand side, it should generally switch back and forth between the types, and that would leave us with, well, from minus infinity to negative 1.63, it's increasing. And it's also increasing from 1.63 to infinity. And then it's decreasing on the interval in between from negative 1.63 to 1.63. And again, this is not exact because we were just using a calculator to do this. There is a way to get, well, what is the exact value? In this case, these are irrational values, so it would be some kind of a square root. And actually, it would involve what's called taking a derivative and applying the quadratic formula. We're going to review the quadratic formula in the next week or so. But at any rate, this is all involving calculus, and I'm trying to give you the the tools and and talk about all the notation that you're going to use. That way it's a lot easier to understand all of these things and what they mean. And also, just a reminder that when we're talking about mins and maxes, we're using a coordinate point notation, right? So it's right 1.63 down. But when we're talking about intervals, it looks the same, but it's not. It's no longer a point. This can definitely be confusing if you don't know, what it means in each context, because we're going back from point notation back to interval notation seamlessly a lot of the time.